All right, next up we will talk about human vision. We'll go ahead and treat components of the eye as a collective lens, and we'll treat the retina as our screen where the image is forming. So that's a simplification, because technically in your eye you have the cornea, you have the iris, and you have the aqueous humor. These all have different indices of refraction, and then you have a lens that has its own index of refraction. We're going to treat these together as one single lens type component, and this is a simplified model. And then we have a screen back here where the image is forming. Notice that objects that we look at are at different distances out here. So you'll have something really far. If you're reading, you have something fairly close, etc. But we need the image to always form at the same location behind the lens. So the question you might have is, how can we see both nearby and far off objects clearly, given that the object distance can really vary quite a bit, and we just have a single lens that we're looking through? It's not like we're replacing lenses in our eye. Well, the answer to that is accommodation. Accommodation, basically muscles in the eye adjust the shape of the lens to change the focal length of the eye, so that the objects at different distances form images on the retina. So what we call relaxed vision is focusing on distant objects. So when you're looking at something far away, this is where the eye muscles are relaxed. And then on the other hand, accommodated vision is when we're focusing on something nearby. The range of distances we can see clearly for somebody with perfect vision is from about 25 centimeters all the way out to infinity. The near point is the closest distance we can see clearly. And one way you can try to figure out what your near point is hold your notes or your screen or whatever in front of your face and keep bringing it closer and closer until you can no longer focus on it. And that's about a 25 centimeter distance. And then in theory, if you have perfect vision, you can see all the way out to infinity. There's of course the diffraction limit or the resolution limit that we run into in being able to resolve objects, but you can focus all the way out to infinity. The near point is the closest distance you can clearly see, and the far point is the farthest distance. So basically, objects that are at a distance of 25 centimeters all the way at object distance going to infinity, we can essentially focus on our retina. So here's a reminder of image formation of converging lenses, because we have a converging lens in our eye, essentially, or our eyes are converging lenses that form images on the retina. So for a converging lens, an object infinitely far away. So when an object is super duper far away, the image forms on the focal point. And then when the eye is relaxed, the retina is at that focal point. And then when the objects come closer, what happens is the image forms behind the focal point. So when these objects come closer, the image might form out here. So what does our eye need to do to that lens to move that image closer to the focal point? So that's basically our first clicker question. So obviously we're not going to do it as a clicker question, but I want you to think through this. What needs to happen to the focal point, or what needs to happen to the rays that are being bent for an image that's forming back here, for that to move closer this way? So go ahead and think about that, pause the video, and once you've thought through it, we'll go through the answer. So the correct answer here is that the lens should get more curved, causing increased bending of incoming rays. So when we need the image to form closer this way, basically you need this ray to bend even further. You need this ray to bend also further, and that gives an image closer to the focal point. So what your eye essentially is doing, the muscles in your eye are giving you a more, basically a higher power, more curved lens to allow the image to still form on the retina. So let's take out the two cases. We have relaxed vision, where the object is somewhere out here at infinity, and the image forms right on the focal point on the retina. And then on the other hand, in accommodated vision, when you have some object at a finite distance, some smaller distance, well, if the lens still looked like this, the image would form somewhere back here. In order to move that inward towards the retina, the power of this lens needs to be greater. The focal length of this thing has to be smaller, so you get a more curved lens that then focuses the image on the retina. So essentially that's equivalent of a thicker lens. So when your eyes are accommodating, essentially the lens here is in a thicker position, whereas when it's relaxed, it's in a thinner position. So let's go ahead and calculate the power of the eye. And by power, we're just asking for in units of diopters. So recall from earlier that power for a lens is 1 over the focal length. So we just want to find the range of focal lengths for the eyes, which will give us the range of the powers for the eye. All right, so let's go ahead and approach that. So we know, well, let's read through the question. So what is the range of focusing power for an eye that can clearly see objects between 25 centimeters to infinity? So basically we're talking about somebody who has perfect vision, and they can look at objects anywhere from 25 centimeters to infinitely far away. And then we're given that the retina is located 2 centimeters behind the lens. So this is our image distance. So we know the image always has to form 2 centimeters to the other side of the lens, which is a positive image distance. And we're going to do everything in meters. So let's go ahead and convert this to meters. So the image distance is 0.02. Okay. So in the case that we're looking at an object that is at 25 centimeters, we know that the object distance is going to be 0.25 meters. And let's go ahead and solve for the focal length, because once we get the focal length, we can get the power using this. So we have 1 over f is equal to 1 over object distance plus 1 over image distance. So we're solving for, and actually 1 over f is exactly what the power is. So let's just replace that with the power. This is equal to 1 over do, which is 1 over 0.25, plus 1 over di, which is 1 over 0.02. And let's go ahead and plug these numbers into our calculator. And after we plug these in, we should get that this is equal to about 54 diopters. So the power for when we're looking at something as close as possible. So if you're thinking ahead, this is going to be the maximum power of your eye, because this is as accommodated as your vision can get, and the power is 54 diopters. Let's now calculate the case for when you're looking at something infinitely far away. So basically d object goes to infinity, and we want to find what the focal length is in that case. So again, 1 over f equals 1 over do plus 1 over di. 1 over f is the power, and then 1 over, if do pretty much goes to infinity, 1 divided by a really big number is essentially 0. And if you're bothered by me doing 1 over infinity, that's good, because essentially we're taking a limit when do goes to infinity. But I'm not going to bother with limits here. We're just going to say, like, if you're dividing by a very large number, then this whole thing goes to 0. Plus 1 over di, and di is still 0.02 meters. That gives us that the power is just 0 plus 1 over 0.02 meters, which is equal to 50 diopters. So the range of power for our eye goes from 50 to 54 diopters. So min is 50, max is 54. And you can go ahead and find also the focal length for when your eye lens is relaxed versus accommodated. So when we're talking about max power, that's basically the most accommodated it can get. So 1 over 54, which gives us 1.85 centimeters. And then on the other hand, when your eye is relaxed, the focal length is 1 over 50 meters, which is equal to a focal length of about 2 centimeters. So the question didn't ask us to get the focal length. The question just asked us to find the focusing power of the eye, which is this range, but you can get the corresponding focal lengths. Okay. So what are some possible vision defects that can happen? And there are two types of vision defects. There's nearsightedness. Your eye could be myopic, meaning the eye focuses image in front of the retina. So instead of focusing on the retina, the focus is happening earlier or in front of the retina. And on the other hand, farsighted, hyperopic, this is a case where eyes are focusing behind the retina. And these are corrected by lenses. So if we're talking about a myopic eye, well, you know that the focus is happening before the retina. In that case, we put a diverging lens in front of the eye. Why is that? Well, these rays are basically bending too much before the image can form. Basically, you want the image to form here, but it's forming too early. So basically what we do is we use a diverging lens to diverge out and to bend outward these rays a little bit so that when they do bend, the image will form back here on the retina. So diverging lenses are used to correct myopia. And you can guess, on the other hand, when you have, so let's go ahead and go to the other case. If you have hyperopic eyes, basically the focus is happening back here. In those cases, we put a converging lens because basically we need to help the eye in bending the rays further and causing the focused image to form here. So farsightedness is corrected by converging lenses, and nearsightedness is corrected by diverging lenses. And I will bring the demo to class on Wednesday for you all to be able to see this.